Okay, so this is the Calc 2 Exam 1 revision questions. And so our first integral is the indefinite integral of sine 7x cosine 4x dx. And we know we can't go ahead and integrate this, so we have to use one of our special formulas or methods to figure this out because these are being multiplied. So an equation I know that we can use is a half angle formula, which states sine of A times cosine of B is 1/2 times sine of A minus B plus sine of A plus B. Okay, and so applying this to our integral, we can rewrite the integral as the indefinite integral of 1/2 times sine of 3x plus sine of 11x dx. So I know I can go ahead and move this 1/2 out. So moving it out, you get sine of 3x plus sine of 11x dx. And now we have it to a point where we can actually go ahead and integrate it. So to integrate sine, it becomes negative cosine. So to rewrite this, we can say 1/2 being multiplied by negative cosine 3x over 3 minus cosine of 11x over 11. Don't forget your plus c. And just to simplify this a little bit more, we can distribute the 1/2 and rewrite it as negative cosine 3x over 6 minus cosine of 11x over 22 plus c. And this will be your final answer. So for our next question, it says, a spring has a natural length of 28 centimeters. If a 28 Newton force is required to keep it stretched to a length of 36 centimeters, how much work, W, is required to stretch it from 28 centimeters to 32 centimeters? Round your answer to 2 decimal places. So to start off this, we need our equation for work, which is f of x equals kx. And so we already know our f of x is 28 newtons. So we're going to have our 28 and set that equal to our k times our x, because we are trying to solve for k. And so we know we are stretching it initially with 28 newtons from 36 centimeters to 28 centimeters. And that gives us 8 centimeters. But because force works in meters, we need to convert our 8 centimeters to meters, which just becomes 0.08 centimeters to meters. And so we can put our 0.08 in here as our x and divide both sides by 0.08. and this will give us 350 is equal to our k. So for the integral, we need to find this. Its work is equal to the integral from a to b of k x dx. So to find our bounds, we need to know that it's going from its natural length of 0 to its new length of 32 centimeters. So you can just go ahead and subtract 32 minus 28 as we did in the first part. And you are going to get 4 centimeters. And once again, we need to convert this, so that gives us 0.04 meters. So your new bounds are 0 and 0.04. And then we already know our k is 350, and you can just bring down your x dx. So we know from here we can go ahead and integrate this because they're just being multiplied. So you can rewrite this as work equals 350 times x squared over 2. So you can put this on top, or you can just leave it off to the side. And keeping your bounds from 0 to 0.04. And so from here we can just go ahead and put in our 0.04, and that will give us 0.04 squared over 2 times 350, which will give us work is equal to 20.28 joules minus, if you put in your 0, that just gives you 0. So we know work now is equal to 0.28 joules. And that is your final answer. So this is question 3 from Calc 2 Exam 1, and it says compute the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1 y equals 0. X is equal to 1 about the y-axis using shell disk washer method. Sketching the region, finding the limits if need be, finding the height and radius of the shell by setting up an integral of the volume of solid, finding the value of the integral. So just looking at this question, I know I'm going to want to graph it first before I decide which method to use. So I'm just going to label this A and grab a graph. And I'm going to go ahead and label this point 1. And I'm going to make this one my other one. So then in here, because we know we're rotating about the y-axis. So to go ahead and draw this, you know you're going to be stopping at 1. So I'm just going to go ahead and draw hopefully straight line at 1. And then I'm going to draw the parabola, which is going to start at 1 on the y-axis because that's your intercept. So it's going to go up like that and up like that. And just to connect these lines, and then I'm going to erase the extra part of the graph I don't need, just to be concise. And just looking at this, I know it's going to be rotated around, so you know this is going to be closed. And just looking at this kind of looks like a cylinder already to me, so I'm going to be using the shell method, which is just taking one shell and revolving it around so you have a bunch of shells and then adding them up. So for part B, finding the limits were given to us. Y equals 0, which is the x-axis, and x equals 1. So that will be your limits. And for C, to find the height and the radius of the shell, you know your height is going to be the equation of the graph given to you. So it's going to be x squared plus 1, and that's our height. And then for our radius, we're going to label it x. And then for D, we can go ahead and move D over here. Setting up an integral of the volume of the solid. The integral we can set up now is the integral of 2 pi from 0 to 1 x squared plus 1 times x dx. And the reason why we have this 2 pi is because it's a cylinder and that's part of the equation. So the next thing we're going to want to do, part E, is to find the value of the integral. So to do this, we're just going to first simplify the integral and then solve it. So we know we can move 2 pi out because it's a constant, and then we're left with x squared plus 1 times x dx. Now from here, you're going to distribute your x, and you're going to get the integral from 0 to 1 of 2 pi, rewrite that, of 2 pi, integrals from 0 to 1, x cubed plus x dx. And from here, you can go ahead and integrate. So rewriting this, we have 2 pi, and now to integrate, you put x to its power plus 1, so that's going to be 4, over n plus 1, plus this x, so this is going to be, this is already x to the first, so your n plus 1 will make it squared, over 2, plus c. And now what we can go ahead and do is add in the limits to simplify this more. So it's 2 pi, and you're going to be putting each limit and then subtracting the other limit. So first we're going to use 1. So 1 to the 4th over 4 is 1/4, plus 1 squared is 1 over 2 is 1/2, minus 0 to the 4th is 0 over 0 is 0, plus 0 squared is 0 over 2 is 0, and don't forget your plus c. And then you can go ahead and simplify this, and you're going to get, let's see, so 2 pi, this is going to cancel out, and then you're left with 1/4 plus 1/2, which can be written as, just go ahead and erase this, 3/4, and then you multiply the 2 times 3, and you get 6 pi over 4, and that is your solution. So our next question says, compute the volume of the solid formed by the region bounded by the graphs y equals sine x and y equals cosine x on 0 to pi over 4 rotated about y equals -2 using the shell, disk, or washer method by sketching the region, finding its limits, finding the radius and or height, setting up an integral, and finding the value of the integral. So for part A, I went ahead and added a graph in, and we'll call this part A. And so I already added a line here at y equals -2 because I know that's the one we're going to be revolving around. And our equations are y equals cosine x and y equals sine x. And so for cosine, we know it starts at 1 and heads towards 0 at pi over 2, so it's going to be headed in a downward direction. And once we reflect it, it'll be just reflecting that across. It'll be mirroring it, so it'll be headed in an upward direction. And for sine, we know that it starts at 0 and heads towards 1 at pi over 2, so we know that this will be headed in an upward direction. And once we reflect it, we know it'll do the same thing, but in its opposite. And just to connect these so we have a shape. So right away, we can see that we have this space here. So we can go ahead and use the washer method to subtract the sine from the cosine. So for part B, to find its limits, we know that they were already given to us because they are from 0 to pi over 4. Let me rewrite this in black just for consistency. And for part C, to find the size of the radius, we can say that we know that there is a space. On this graph, we can see that there's the space here, which is 2. So to rewrite these, we know that the first one will be 2 plus cosine x, and the second one should be 2 plus sine x. And for part D, to set up the integral, we know it's going to be on 0 to pi over 4. And the equation for the washer method tells us to do pi times r1 squared minus r2 squared. So our r1 is going to be that 2 plus cosine x, because it was the line on top of the graph, and we're going to square that, minus our r2 squared, and so this is going to be 2 plus, this is going to be sine x squared dx. So this next step, all I'm going to be doing is simplifying this. So we know it's still from pi over 4, and it's going from 0, and we know pi is the constant, so we can go ahead and move it out. And then I'm just going to I'm going to square both of these. So I'm going to write 4 plus 4 cosine x plus cosine squared x minus 4 plus 4 sine x plus sine squared x dx. So now we're just going to cancel out anything we can cancel out and move the move things together that can go together, so it's just a little bit more simplified. So we know that this 4 minus 4 will just cancel out, and you'll be left with 4 cosine x minus 4 sine x. And it's subtracting that because this will be multiplied to all of these, and that's also how I was able to cancel out this 4. Plus cosine squared x plus sine squared x. So I'm going to rewrite this. Oh, forgot my dx. So the next thing we can do is we can actually go ahead and use an identity that we know for cosine squared x plus sine squared x. So I'm going to go ahead and write this down. And we know that those two can become sine 2x, or cosine 2x, sorry. Dx. Now we can go ahead and integrate this, and we'll write pi times 4 sine x minus 4 times, and this will become positive, cosine x plus sine 2x over 2 on 0 to pi over 4. So the next thing we're going to do is we are going to plug in our bounds, and in doing this we will have 4 times root 2 over 2 plus 4 times root 2 over 2, because cosine at pi over 4 is root 2 over 2, plus 1/2, because this with pi over 4 will become 1/2, pi over 2, and sine of pi over 2 is 1, so you'll have 1 over 2. And then we're going to be subtracting that by whatever 0 gives us. So 0 at sine x is 0, or sine of 0 is 0, times that 4 would be 0, plus 4 times cosine of 0, which is 1, will be 4, plus sine of 2 times 0, so 2 times 0 is 0, so sine of 0 is 0, over 2 is 0, so we can go ahead and leave those other ones off. And just to simplify this further, we will now have 4 root 2 over 2 plus 4 root 2 over 2 plus 1/2 minus 4, or we can simplify this 1/2 minus 4 to 3/2, and then we will have pi times 8 root 2 over 2 plus, or actually this should be negative, that should actually be minus 3, so then you will have minus 7 over 2. And now you will be left with pi times 4 root 2 minus 7 over 2 And let's see if we can actually simplify this more. So minus 7, I'm going to go ahead and type it into my calculator. And this just gives us the same thing. So we will have 4 pi root 2 minus 7 pi over 2. And that should be your answer. So for our next question, we have solve the indefinite integral of sine square root of x dx. And to start this one out, I'm going to be doing a substitution because I know I have something in parentheses, and that's how I would start. If you know you have something in parentheses, it's easy to try. And it's a quick method to see if you're going to be wrong soon and if you have to change your method. So to start, I'm going to have a t, and I'm going to set it equal to what's in parentheses, so square root of x, and then my dt is going to become 1/2 x to the negative 1/2 dx. And so I know I have to simplify this, so to do that I'm going to multiply by 2 so that the 2's will cancel out, and then I do that same thing to the other side, so now I have 2 dt equals x to the negative 1/2 dx. And I know I can't leave this x over here, so I'm going to move it to the other side, which will make the exponent positive. So I have 2 square root of x dt equals dx. So this negative 1/2 basically tells us that it's negative square root of x, and when you move it to the other side it becomes positive square root of x. And this actually helps us because we know that t is the square root of x, so we can just put that in. So we will rewrite this again as 2t dt equals dx. And so now we know our t and we know our dt. And so applying this back to our integral, we can rewrite our integral as the integral sine of t 2t dt. And so now basically to simplify this, I'm just going to rewrite it so it's more concise. I'm going to rewrite it as 2t sine of t dt. And so I know I still can't integrate this, but I do see that we have 2 factors here, so I'm going to try a integration by parts. And to do this, you need to know the equation u v minus the integral of v du. So in this case I'm going to rewrite these now. So our u is going to be 2t, and that makes our du 2du, and our dv is going to be sine of t, which makes our v negative cosine of t. Okay, so to rewrite this in this form, we are going to say the integral of 2t, or we don't need that integral sign yet actually, so it's going to be 2t times negative cosine t minus the integral of negative cosine t times 2 dt. So this is now our new integral, and we can rewrite this part because this part's just going to come along for the ride. Sine t. And this integral, now this negative sign will become positive. So plus sine of t, and then we'll just move this over here. So it's plus 2 sine of t. Now we're going to go ahead and put back in what our t value is, which we wrote as up here as t equals the square root of x. So to put that back in, we will have 2 square root of x times negative cosine of the square root of x plus 2 sine square root of x. And now everything is back in terms of x, and everything is integrated. So that's it. Okay, so our next question is to solve the integral of cosine x times cosine to the 5th sine x dx. So just by looking at this, we know we can't go ahead and integrate because this part is together and it's being multiplied by this part. So what we can do is try to choose an integration method. So going through them, I think we can try a u-substitution. And we can have our sine x as our u, and our du will be cosine x. So applying this to our integral, we'll rewrite this as the indefinite integral of, this will be marked off by this. So we can add that at the end, we'll add our du, and then this goes here as our u. So we will rewrite this part as cosine 5u du. And so we know we can integrate this because this is to the 5th and we don't know how to integrate that. So we will rewrite this again just to simplify it into a way we can integrate as cosine u times cosine to the 4th. Let me rewrite that. To the 4th u du. And we just pulled out 1 from this, and that's important to remember. So we know that they're equal, but we want to try to find a way to change one of these into something we can cancel out. So we can change this to make it look like something we know. So we know the first one we can keep the same as cosine u, and then we're going to rewrite the second one as cosine squared u squared du, which can turn into the integral of cosine u times 1 minus sine u squared du. And this is a Pythagorean identity. So So now we can go ahead and do another substitution so that we can cancel one of these out. And the substitution we're going to make, we'll use t as our variable, and we will make t sine x, or sine of u, since we changed our variable. And our dt will be cosine of u. So now, putting this back into our integral, we can rewrite this as cosine of, cosine of u will actually be canceled out, and I forgot my du here. So this right here will cancel out this and this, and we can just write on the end of our integral dt, and we know that now we will have 1 minus sine squared. Let me move this back. Sine squared, or no, it'll be 1 minus t squared, the whole squared, dt, because this becomes this and this, just as your little reminder. Okay, so now we actually know how to integrate this. The first thing we're going to do is expand it by squaring it, by taking this and actually multiplying it out. And if we multiply it out, we will get 1 minus 2t squared plus t to the 4th dt. Okay, just to give us a little more room. So once we take the integral of this, what we get is 1, or the 1 becomes t minus, and we transform this 2t squared into 2 over 3 t cubed plus 1/5 t to the 5th. So what I just did was I added 1 to the exponent and put the number in front over that number. So this 2 right here became a 3, and I made it 2/3. And same with this one, this 4 right here became a 5, and I put 1/5 because you have a 1 as your constant in front of the t. And then don't forget your plus c. And then what we can do from here is put it back in terms of u. So I will zoom out so we can see our things. And this now becomes sine of u, because that's what we said our t was. Sine of u minus 2/3 sine cubed u plus 1/5 sine to the 5th u. And now, just to put that back in terms of x, so we have it fully simplified. Oh, don't forget plus c. So putting it back in terms of x, you would get sine, and that u becomes sine of x. So sine of x minus 2/3 sine cubed sine x plus 1/5 sine to the 5th sine x. Plus c. And this right here becomes your final answer. Oh. And that's how you do it. So our next question says, solve the integral of x cubed times the square root of 1 minus x squared dx. So we know we can start off with trying a substitution, and I see immediately that this looks like a trigonometric substitution. So this looks like, let me use a different color, the square root of a squared minus x squared, because we have our a squared and our x squared. And in the equation, this becomes a sine theta equals x. And so for us, this will be 1 sine theta equals x. And our dx will be 1 cosine theta d theta. So putting this back into our integral, we can replace all of our x's now with sine. So we will have sine cubed theta times the square root of 1 minus sine squared theta. And we have to add in this cosine d theta for our dx. So this dx becomes cosine theta d theta. So now what we're going to want to do is rewrite this in a way that we can get it closer to something we know to simplify. So we can rewrite this as the integral of sine cubed theta times, and we know that 1 minus sine squared, due to our Pythagorean identities, becomes cosine squared. So this will become cosine squared theta times cosine theta d theta. Okay? And just to simplify this some more, we can say that this squared right here will knock off our square root, and then we will multiply these together. So you will have just cosine because of this, and then when you multiply them, it'll become cosine squared. So you have sine cubed theta times cosine squared theta d theta. And now we have this integral, but we still can't integrate it, so we are going to find another way to simplify this even more. So we can write this as the integral of sine squared theta times sine theta times cosine squared theta d theta. And once again, we know that sine theta is equal to 1 minus cosine theta, so we will replace that. Cosine squared theta. And it's still being multiplied by a sine theta and a cosine squared theta d theta. So now what we can do is, to simplify this more, we can have a u-substitution, and our u can be cosine theta, and our du can be negative sine theta d theta. So we will put this into our integral. So this sine theta d theta will cancel out this sine theta and that d theta. And our cosines will become u now. So we will have 1 minus u squared times u squared du. And you don't want to forget this negative, because that negative is very important. So we just put it out front. So we can go ahead and simplify this and then integrate. So to simplify this, you will distribute the u squared to both of them, and you will get this negative u squared minus u to the fourth and don't forget your du. And once you integrate, you will have u to the third over 3 plus u to the fifth over 5 plus c. And so what we're going to want to do is put this back in terms of cos of theta. So we will go back to our u-substitution and just put this in terms of theta. So our u's become cosine thetas. And this will be cosine to the fifth theta plus c. And we're still actually not done, because if you remember, the original equation was in terms of x. So we're going to have to put it back in x. And the way we're going to do that is by drawing a triangle and figuring out what cosine is in relation to what our sine was. I'm just going to draw a triangle. So what we said in the beginning was that 1 sine theta is equal to x. So we know, because of SOHCAHTOA, sine is equal to opposite over hypotenuse. And so we know that once we divide this by 1, both sides by 1, you will have x over 1. So you will have your 1 as a hypotenuse and your x as a side, as your opposite side. So just using Pythagorean identities, we can solve for this. So you will have 1 squared is equal to x squared plus a squared, and we're solving for a. And then I can go ahead and just subtract x squared, and it's 1 minus x squared equals a squared, and we're solving for a, not a squared, so we're going to want to take the square root of both sides. And you get that a is equal to the square root of 1 minus x squared. And the reason why I dropped this squared right here on the 1 is because 1 squared is just 1. And one way you can check to make sure you did this correctly is that it should match up with your original answer when you're solving for a. But that's for sine. So now we know this other side, your adjacent, should be 1 minus x squared. But to solve for cosine, I'm going to write it over here. So cosine is adjacent over hypotenuse, and we know our adjacent now. So cosine should equal square root of 1 minus x squared over our hypotenuse, which is just 1. So we can go ahead and put this in for every cosine in our integral. So just to do that, this will become the square root of 1 minus x squared and just the top is going to be cubed over 3 plus the square root of 1 minus x squared to the fifth all over 5 plus c. And that c is just our constant because we weren't given bounds. And so that is your solution.